What if everything you thought about the moon was wrong? Not slightly off. Fundamentally wrong. Because NASA just discovered something beneath the lunar surface that changes everything we know, not just about the moon, but about how worlds are built across the entire universe. And it starts with one impossible observation. For as long as humans have existed, we've stared at the moon. Same face, same craters, same dead, silent rock hanging in the sky. At least, that's what we assumed. At NASA's Jet Propulsion Laboratory, planetary scientist Ryan Park and his team shattered that assumption completely. Using data from NASA's Grail mission, Park tracked two spacecraft, nicknamed Ebb and Flow, as they orbited the moon in 2011 and 2012, flying just tens of kilometers above the surface. These twin probes measured the moon's gravitational field with insane precision, detecting shifts smaller than the width of a human hair. And here's what nobody expected. The moon was moving, its surface rising and falling by up to roughly a foot with every orbit, squeezed by Earth's gravity like a stress ball in invisible hands. Scientists call this tidal deformation. Right now, as you watch this, the moon is expanding and contracting in a slow rhythm set by Earth's pull. But that wasn't the shocking part. Stay with me. When Park's team analyzed the data closer, they found the moon wasn't flexing evenly. The near side, the face locked permanently toward Earth through a phenomenon called tidal locking, bent dramatically more than the far side. The pattern was asymmetric, strange, and completely unexplained. Something hidden beneath the surface was making one half of the moon softer than the other. And what they found next, nobody saw it coming. When spacecraft first photographed the far side of the moon in the 1960s, astronomers were stunned. The familiar side, the one humans have gazed at since before recorded history, is covered with vast, dark plains called Maria. Smooth seas of ancient cooled lava stretching across nearly a third of the surface. But flip the moon around, completely different world. Rugged, battered, cratered everywhere. Almost zero volcanic activity, only about 2%. It looked like the moon had two completely different personalities, one shaped by fire, one frozen in time. Scientists spent decades trying to explain it. Maybe Earth's gravity-focused eruptions on one side. Maybe the far side's crust was too thick for magma to break through. Nothing fit. And now Park's gravitational data revealed something even deeper. The near side wasn't just different on the surface, it was different inside. Something beneath it was warmer, softer, more pliable. The moon wasn't a uniform ball of rock. It was a world with two faces and two very different interiors. So what was hiding down there? This is where it gets wild. Beneath the near side, buried deep in the lunar mantle, Park's team identified massive concentrations of radioactive elements: uranium, thorium, potassium, elements that generate heat as they decay, slowly releasing energy over billions of years. Scientists believe this happened during the moon's violent birth. Around 4.5 billion years ago, a Mars-sized world called Theia slammed into early Earth. The debris from that collision coalesced into the moon. But the radioactive material didn't spread evenly. Models suggest it pooled heavily beneath one hemisphere, the side that would eventually lock facing Earth. The result was essentially a natural nuclear furnace, a hidden heat source that kept the near side's interior warm, soft, and flexible, while the far side cooled into cold rigidity. This radioactive heart explains everything. The volcanic Maria seas, the asymmetrical flexing, the moon's split personality. And here's what's extraordinary. That furnace is still running. Right now, radioactive decay continues generating heat beneath the near side. Every 27 days, as the moon completes its orbit, Earth's gravity squeezes this warmer hemisphere more dramatically than the cold far side. The moon isn't the dead rock we were taught about in school. It's still responding to forces set in motion 4.5 billion years ago. But to prove all this, NASA had to pull off one of the most precise experiments ever attempted in space. The twin Grail spacecraft, each roughly the size of a washing machine, flew as low as 23 kilometers above the lunar surface during their extended mission. That's absurdly close. They skimmed past mountains and crater rims, constantly adjusting to avoid crashing. Between them, microwave signals tracked their separation distance down to a few microns. Whenever one probe sped up or slowed due to hidden gravitational variations below, the other detected it instantly. Park's team fed this data through NASA's most powerful supercomputers, filtering out every possible disturbance: solar radiation, thermal effects, even the gravitational tug of distant planets. What emerged was the most detailed gravitational map of any world beyond Earth. Buried valleys, dense rock formations, and the asymmetric flexing patterns that revealed the moon's radioactive heart. No telescope could have seen this. Only gravity told the truth. Here's why this matters beyond the moon. Mars has the exact same problem. Its northern hemisphere is smooth lowlands. Its southern hemisphere is rugged, cratered highlands, kilometers higher in elevation. Scientists call it the Martian crustal dichotomy, and after decades of study, nobody fully understands it. Then there's Io, Jupiter's volcanic moon. For years, astronomers assumed its eruptions came from a global ocean of magma. But gravity data told a different story. Scattered pockets of molten rock, like hotspots beneath solid crust. Pattern after pattern, the same lesson emerges. Planetary bodies don't form neatly. They form violently, asymmetrically, chaotically. The moon's lopsided radioactive heart isn't a quirk. It might be the rule. And that changes how we think about every rocky world in the galaxy. For centuries, scientists assumed planets and moons formed in orderly stages. Heavy stuff sinks to the core. Radioactive material spreads evenly. Heat dissipates predictably. The moon just proved that model is broken. If a single collision can permanently divide a world into hot and cold halves, active and dead, then what about the billions of exoplanets scattered across the universe? How many of them are lopsided, fractured, carrying hidden furnaces that reshape their surfaces in ways we've never imagined? And this isn't just theoretical. It has consequences right now. NASA's Artemis program plans to land astronauts on the moon and eventually build permanent bases. Those missions must account for the moon's complex gravitational field. Without precise maps, landers could miss their targets by miles. The asymmetrical flexing also creates stress across the crust, triggering moonquakes. Future habitats need to be engineered for seismic activity on a world we once thought was perfectly still. The moon we're returning to is not the moon we left in 1972. So here's the new picture. The moon is not a dead rock. It's a dynamic world, still shaped by an ancient catastrophe, still flexing under Earth's gravitational grip, still warmed by radioactive fire deep beneath its surface. Every orbit, every tide, every hidden quake tells the same story. The moon remembers its violent birth, and it has never stopped changing. If our closest neighbor, a world we thought we understood, still hides secrets this profound, what else is waiting to be discovered? Next time you look up at the moon, remember this. It isn't just reflecting sunlight, it's flexing, shifting, carrying the scars of a collision that still echoes 4.5 billion years later. If this changed how you see the moon, subscribe. We break down discoveries like this every week, things hiding right above our heads that most people never hear about. Drop a comment. What surprised you most? The radioactive heart, or the fact that the moon is still flexing right now? I'll see you in the next one.